To start with this discussion about state and algebraic variables, we're going to start discussing the basic terminology that we use here in modeling of environmental systems. So here we have discussed a variable and we have used the term variable. And for the further discussion of this lecture, we're going to again give the definition. And this is a value that changes freely in time and space. And a state variable is one which represents a state. So if a variable moves freely in time and space, it means that this is a dynamic variable, right? Just please remember that we are now omitting the space because we are working only with a function that only, a variable that only changes in time. The systems that we have discussed, we also have constant terms, and these are terms that do not vary with the system under study. For example, acceleration due to gravity is a constant, and in most of the air-based environmental models, and these are the ones who actually we're gonna discuss here. But we have other constant values that, like for instance, the ideal gas are a constant term, and there are other constants that are kind of universal, right? Do not change in any space that we are discussing, in any condition, system that we will be discussing. Then we have parameters. This is a term that is very familiar with we have gone through this term before. So parameters are kind of also fixed values. We distinguish from the constant values because parameters can be also found experimentally, or can be only for the conditions of the system that we are dealing with. Okay, so the definition is that a parameter is a value which is constant in the case concerned but may vary from case to case, where a case can represent a different model run or different grid cells or objectives within the same model. So now that we know, we have again clarified what is a variable, we now going to go further into detail about state variable. And this is related to the stock. So remember that the stock is an extensive variable, right? It can be the mass of a component, it can be the energy of a subsystem, and the stocks are the first step on defining the system. But the stocks or the state variables is actually a variable that will depend on inputs and outputs to have a change. So it is a compact and concise representation of the previous history of the system, and it's like you have to define it at time 0, and then the inputs and outputs will give you the following behavior of the state variable at the following time steps, right? So the state of a dynamical system is a minimal set of variables, and the knowledge of these variables at the time 0, together with input for these and outputs, determine the behavior of the system. So a differential for this, therefore, a differential equation is required for each state variable to describe a system. And how can we also distinguish this from a flow? Well, a flow is also a flow, or a transformation is something that depends on a parameter, on a rate, right? Like it's constantly evolving. While a state variable, which is a stock, is something that we have at some point in time, and then it will change depending on the influences that are affecting our system, right? So we have as an example in the heat conduction problem from the problem set on week 3, we have actually two state variables, which were the enthalpy of the hot body and the enthalpy of the cold body. And then we also have these examples again. Well, one of the energy example on the projects that we have, the project that we have gone through, right? So now we are going to define what is an algebraic variable, and this is similar in terms of that is also a function that it's time dependent, and it will change over time depending on the influences in the system. The difference here on the algebraic variable is that it can be a flow, or it can be also an equation that is being required for that is dependent on the stock, right? So the key feature of an algebraic variable, and keep in mind this because this is very important to understand them, the key feature of an algebraic variable is that within the equation to estimate this algebraic variable, a stock is included. All right? So for instance, if we're talking about the example on the difference in on the room differences of temperature depending on the wall, on the material of the wall, we have identified, we have as algebraic variables the temperature of the hot body of the hot room, and the temperature of the cold room, and we also have a flow as an algebraic variable. This flow is dependent on the stock. This is the this one is the heat, right? The heat transfer, of due to conduction, right? And this one is actually not straightforward, because if you see it, it does not include directly the stock, but it includes one variable that actually has to go through the stock to be calculated, which are actually both variables: the temperature of the hot body and the temperature of the cold body. Now, this is the way when you look at the equations options, the equation windows in STELLA, you will see the way that the state variable is being calculated. And then also we have the algebraic variables. This is very important now for you to visualize how these are estimated, but also why these are state variables. So if you see in the enthalpy of the cold body, we have at one time, and then it's been calculated from a previous time step. So it says H cold T minus dt plus the flows. And the only flow that we have is actually the heat transfer, right? We also have an initial condition, an initial enthalpy, because we need to know the initial condition of the stock. We have the inflows, and then the calculation of the algebraic variables that are actually at the bottom, also aside of the heat transfer, are at the bottom, which include the temperature of the cold body and the temperature of the hot body. In a similar way, we will see that the concentration of when we're talking about mass, or we're talking about concentration of a pollutant in a lake or in a river, or concentration of nutrients, as we have mentioned before, we will deal with mass and we won't deal directly with concentration, but we will have an equation to estimate the concentration. And again, we also this concentration is an algebraic variable. Another example, interesting example, is the estimation of the surface area. So the variation of the surface area is dependent on the volume of water in the system. So calculating these algebraic variables can be seen as something that is very straightforward. Why are we spending so much time on the definition of these algebraic variables? There are two main reasons, and one is that these are not always straightforward, and the calculation actually requires for you to understand that these are also dynamic variables that also change in time. well, in our case, only in time, and that's why we are not calling them in terms of vectors. And also because there are sometimes, in some cases, there are no explicit relationships that exist between the state and the algebraic variable. So we may not have an equation, and what we will have is actually a function that has been described in segments. And another reason for not having a straightforward way of calculating these variables is that they might be coupled in complexly nonlinear equations where it is difficult to derive explicit expressions for each algebraic variable. So the situation is more complex, and what we are going to discuss in this session is only about when is the case where we actually have a piecewise continuous or segments of this material or information to construct or to know these algebraic variables. So this is one example, and this example is related to the surface area of water at time t. This is an algebraic variable. It's a function of the volume, but it's actually, we don't have an equation for this. If we will have, let's imagine that we have a system, a lake that has a cone shape, then we will think, well, we can estimate actually the area depending on the volume based on geometry, right? This is what we have done actually for the estimation of the area, the transfer of heat in the project number 1, right? But what if we have only the data about how the area change with the depth and with the volume? Then it means that we have to actually incorporate this information into our model. This can be easily done by in STELLA. So in STELLA we can actually have even a graph. So a graph can actually have a can give us the information of the algebraic variable. So this will be the case of the example of the Easter Island, where we have harvesting per person, and this is described as in a graphical mode, where we have harvesting per person as a function of coconut palms, and also divided by the initial amount of coconut palms. So we can have graphics and we can also have table inputs on STELLA. So now let's think about how can we enter these parameters when we are using MATLAB. That will mean that we will have to match the time entering a function that estimates this or extracts this value from a table as well. Or in the case of if it's a function of time like rainfall, we will have to match at each time that we have a value that the model extracts the information.